Right, the node architecture that we developed, you see the systems here, it's just one circuit board, but lots of sensors. And we put 2 of these into the commercial systems. So again, similar to avionics, you've got an FPGA or an ASIC on one side, and another side, an MCU. The FPGA provides the basic safety layer and manages half the sensors. The sensors are very redundant, so they share with each other the information from those sensors, and they each have enough sensors to run the entire system. The ARM MCU provides the monitoring, optimization, and can take primary control. So rather complicated protocols. So if the FPGA does not respond in time, then the MCU can challenge it saying, you've got to respond. Are you working? And if it still doesn't respond, it can then go into a stage where it takes control of the system. So the code on that becomes critical code. And it's quite a large system. 120,000 lines of code in Maestro C. In addition to that is a lot of Verilog code. The sensors are not too wonderful either. We did a long study on the sensors. The oxygen sensors, which we rely on, we tested them for all the suppliers and couldn't find any that worked reliably. The number of failure modes really quite astounded us. And so we've got 8 of these sensors where we need one that works. And we, of course, the system self-tests, checks the sensors, it checks the actuators, and everything's very closed loop. But that was adding an extra layer of complication to this. So the software architecture, at SIL 3 and SIL 4, it's extremely difficult to get away with anything except a time-triggered architecture. So a task scheduler generates automatically from task durations and interval requirements is executed such that you've got a startup procedure which has to very rapidly see, is the diver breathing from this? If so, make sure he's alive. So there's no on-off buttons to start with. An interesting fault another company had on their own rebreathers, the same one that had the no watchdog, was that somebody tried using it for commercial diving, and they used a jackhammer. There's an on-off button. Guess what on-off buttons do when you vibrate them? They turn off. In addition to that, the accident study, which found literally hundreds of dead people, ranging from Nobel Prize winners to really gurus in the industry, the slaughter on these units is really quite remarkable in the sports sector. The unit also does not switch on. Their unit does not switch on automatically, and so when you're breathing from this, you're not aware at all that it's not on unless you look at the displays. So people were jumping off boats with these things not switched on, or they jumped off the boat and it would reset itself when it hit the water. It's really quite an interesting tale. There's an excellent paper called Unskilled and Unaware of It. You just search from Google for that paper. It's about, it's so simple, functional safety, isn't it? Everyone knows how to do it. But people who've not trained in functional safety are not aware of what's needed. And if you're not aware of what's needed, those skills that tell you you need these things, you don't have. So you're not aware that you have to put these things in. So this is a really interesting structure, a lot of it dominated by this accident study data, what people actually do with the system. Because what they do is what matters. In 61508, you're concerned very much not just what the system should do, but what does it actually do when you jump off a boat with it? What do people really do? And what they really do is very, very different. It's like jumping off with them switched off. So here there's a layer which says, first of all, is someone breathing from this? If so, keep them alive immediately. The next one is the is a command processor with USB. Now, to have any USB functionality, you have to have USB power, because it's rather difficult to have USB within a TTA architecture. So that's the way we manage that. So afterwards, to download data, we have a non-safety critical function, USB, and you plug the power in, it powers that up. And it then still checks that no one's breathing on it, the equipment is not under pressure, and things like this. And so there's this section here. The rest of it is a task scheduler, a system retest, system self-test, the various peripheral driver layer, and algorithmic modules. Now, the purpose of the scheduler is to trap and log any rogue behavior. It rations all tasks to execute in their right time and prevents any overruns in time. So if one piece of code has become modified, then that causes a hang, modified for any number of reasons. A big enough lightning discharge can usually modify some code somewhere. Flash memory, after 10 years, it decays a bit. For whatever reason. It traps any incorrect interrupt vectors, because we're not using interrupts to run this system, other than the timer that says, check all the tasks according to the schedule. And it traps attempts to execute any non-sporting codes. So even if the code is perfect, you need these layers, because the real world has these funny things that happen to programs. If you put in very, very short glitches on your power supply, watch what your processor does. You may have verified all your code, but that processor is going to jump about. This controls that. I know you know all of this and do this routinely, but it's worth bringing out. So this is the task scheduler. It's more detailed in your handout. So the tasks that are built up, task plans, each task obviously has a name, the mode it needs to execute in, how frequently you need to call it, its priority, the maximum burst period, the maximum number of times that code should have been running in a certain period of time. The and various other reference functions that are listed in the handout. Out of that information, the task schedule is built up automatically. And that whole task scheduler is something which was written in Maestro C, and we wanted to convert into Spark Ada. And this came about because our processes are our design process is quite manually intensive. In simple terms, it has these 8 steps. We take a formal spec. The word formal means different things to different people. Unfortunately, in our formal world, we have nasty things called analog sensors. So what we do is we simply model what we believe to be the correct function and the environment in a lot of detail. Simulate that to get some confidence that it's correct. Use the various test benches, look at the coverage analysis, validating the specification. So we've heard the various things we've been told by the customer. When we do this, we often find lots of new things that people didn't know about that we have to put in the specification. And those requirements are then formally tracked. We just use a Mantis system to do that. So we're able to formally track all the different requirements that come out of here. There's a written specification as well. So we don't transfer the formal model to software engineering. We like to keep the formal model in a bag. Software engineering are not allowed to see the formal model. They see what everyone has agreed and understands, which is this, and a whole list of these Mantis formalized requirements, very atomic requirement. It must do this function with this spec. From that, they generate a UML spec and models, which we then check against this, against the formal model. They do the code design. Now, for coding, we were using Maestro C in a C++ environment. And that is really limited to SIL 3. You can't get above SIL 3 using Maestro C. The target was to take this eventually to SIL 4 and get it certified for 615 to SIL 4. And so no portable system like this had ever been certified to SIL 3. And so it's quite an ambitious goal. There's a Chinese wall, exhaustive testing, usual things, 100% branch, statement branch and term coverage, separating within the software team the people who are actually developing the code from those who are first of all validating and verifying the code. At the sub-project level, the code is validated to check that it does what's intended to do by the customer. And then after that, there's an independent exhaustive verification that the code does the same as the MATLAB spec. And this is exhaustive. This is where the time goes. We don't use automatic code generation because it's easier to generate all the test cases if you code manually. The verification and validation is repeated as each block's assembled up to a system level. So it's very manually intensive. The validation and verification is expensive. Got a rough rule of thumb. If I start a new project, I'll look at how much it takes to design and construct and build it, and I'll multiply it by, take that, and so I'll need twice as much as that to verify it, validate it, and make sure it passes the spec. And it's interesting, even when Concorde was designed, that's the rough rule they used as well. And so, general rule in projects, if you've designed and built it, my second rule of engineering is that if it's not been tested, it means it doesn't work. And the amount of resource you need to actually test it and discover that it doesn't work and fix it and test it again is twice as much as what you originally started with. So it really is manually intensive. We have a requirement for 100% test coverage, and that dominates the code design, the whole way we design and structure the code. And that helped us a lot, because when we moved from MITRE C to Spark Ada, and we developed the MITRE C basically in a very object-orientated way, and that means that we're able to layer things very nicely. It meant that when we were doing this conversion, we didn't just convert the code statements. We looked back to this level, but the structure we had at that level, thinking to generate MITRE C, turned out to be the same structure we needed to generate Spark Ada.